Hello and welcome back to the Sam Ellis Academy. This is the third and final video in the bonding topic, and today we're going to be looking at shapes of molecules. More specifically though, what we mean by shapes of molecules, the shapes that you need to remember the names of for the A-level, and how you're going to work out the shape of any molecule, even if it's one you've never seen before. Let's begin. Okay, so first, what do we mean by shapes of molecules? It's very easy to imagine these molecules that we draw on a frequent basis, like ethane and hydrochloric acid, as two-dimensional shapes. But we live in a three-dimensional world, and therefore, these molecules exist in three dimensions as well. You'll never be asked to explain why a molecule is a certain shape. All you'll be expected to do is draw a shape of a molecule, whether that molecule be unknown or one that's very common to you, like ethane. And don't worry, there is a step-by-step process for this. Give the name of the shape and give the bonding angle. The bond angle thing will make a lot more sense as we go further into the video. You'll also be asked to explain the difference between a bonding and a non-bonding pair of electrons. Again, this will make sense as we progress. The basis of figuring out the shape of a molecule comes from the amount of valence or outer electrons there are. If you take a molecule, figure out how many electron pairs it's got, figure out how many of them are then bonded or lone, more on this slightly later, you then quite literally refer to a list which tells you for that situation, i.e. 3 bonding pairs, 1 lone pair, what the shape will be. We'll walk through all of the possible situations you can have at A-level, but first I'm going to explain how you figure out how many bonding and lone pairs of electrons there are on a molecule, and what the difference between a bonding and non-bonding pair of electrons are. We'll take ammonia as an example, but this is exactly how you find the pairs of electrons on any molecule. First, look at the central atom. What group is it in the periodic table? That's how many electrons it has in its outer shell when it's by itself. Nitrogen is in group 5. You then look at the atoms that are bonded to this central atom. In the case of ammonia, there's 3 bonded to the central atom. You then take that number 3 and add it to the 5 electrons that exist already. You're left with 8. To find out how many pairs there are, you divide that number by 2, obviously. So in the case of ammonia, there is 4 valence electron pairs. We'll see how the 3D shape relates to this information soon. Spoiler alert, it looks like this. But first, we're going to visit the distinction between bonding and non-bonding pairs of electrons. Lone and non-bonding are interchangeable. If we look at ammonia, you can see that there is 3 covalent bonds. Because by definition, a covalent bond is a shared pair of electrons, this means out of the 8 valence electrons on an ammonia molecule, 2 of them aren't bonded because there's only 3 covalent bonds. 3 times 2 is 6. Therefore, there is 1 lone pair of electrons. On this diagram, they're not noted down, but if we bring back that spoiler from earlier, you can see that the lone pair is denoted by these 2 dots. We'll see plenty more of this later. That, though, is your distinction between lone and bonding pairs of electrons. And it's important that you know how to distinguish the amount of lone pairs and the amount of bonding pairs on any molecule. Let's practice what you've just learned. I want you to find the amount of lone and bonding pairs on boron trifluoride, BF3. Find the group of the central atom. Boron, it's group 3. Count how many atoms are bonded to it. 3 in this case. Add the 3 electrons from boron to the 3 electrons from the bonding atoms. You get 6. Divide by 2 to find 3 electron pairs. As you can see by the fact there's 3 fluorines bonded, there's 3 bonding pairs and no lone pairs. Let's do the same thing with phosphorus trihydride, PH3. Phosphorus is in group 5. There is 3 things bonded to it. You add 5 and 3 to get 8. Divide by 2, you've got 4, which means there's 4 electron pairs in total. But we can tell from the fact that the molecular formula is PH3, there's only 3 actual covalent bonds. That obviously leaves a pair of electrons not bonded. This is a lone pair or a non-bonding pair of electrons. As I said earlier, depending on how many lone pairs you've got and how many bonding pairs you've got around the central atom, you get a different shape. And as I said right at the start, AQA are not interested in why the shapes are how they are. They're simply interested in you being able to figure out the shape of a molecule, whether it's known or unknown. When I said there's a list, I was being serious. We're going to run through every single situation you could possibly have in terms of total bonding and non-bonding pairs. It's one of these unfortunate moments in chemistry where you've just got to remember. We start when you've got a central atom with 2 electron pairs. There's only one scenario you can have here, and that is where both of the electron pairs are bonding pairs. The name of the shape is linear, and the angle between the bonds is 180 degrees. Beryllium chloride is an example. If you've got a central atom with 3 electron pairs, there's 2 situations you can have. An example like boron trifluoride, where there is 3 bonding pairs and 0 lone pairs. In this case, the name of the shape is a trigonal planar, and the bond angle is 120 degrees. The other situation would be 1 lone pair and 2 bonding pairs. It's a great example to explain the difference between a bonding bonding and a non-bonding pair of electrons when it comes to repulsion and bond angle. If we look at BF3, you can see it's 120 degrees between each bond. However, in CH2, the angle between the bonding pairs is decreased by 2.5 degrees relative to BF3's situation, where all of the pairs are bonding pairs. This is because lone pairs repel more than bonding pairs by 2.5 degrees. Now that's understood, the name of this is a bent linear shape. The angle, as I've said, is 117.5 degrees. And you draw it like this. Now we come on to central atoms with 4 electron pairs. The first situation is something you're going to draw a lot of, and that's where we've got 4 bonding pairs, no lone pairs. This is called a tetrahedral shape. The angle is 109.5 degrees. This brings into the spotlight the conventions for drawing 3D molecules. Dashed lines represent back into the page, wedged lines represent out of the page, and straight lines, as you can see, represent in the plane of the page. The next situation we can have is 1 lone pair and 3 bonding pairs. The name of this shape is a trigonal pyramid, and the bond angle is 107 degrees. The final situation with 4 pairs of electrons, 2 lone pairs, and 2 bonding pairs. This actually happens in everyone's favorite molecule, H2O. The name of the shape is bent or non-linear. The angle between the H and the H is 104.5 degrees. Next, central atoms with 5 electron pairs. If we've got 5 bonding pairs and no lone pairs, like we do in the case of phosphorus pentachloride, the shape is called a trigonal bipyramid. That's because the triangular base of 2 pyramids essentially exists in the middle, and you can see what I'm saying here with the pen and the lines I'm drawing. The angles you need to know are the 120 degrees between these atoms and the 90 degrees here. The next situation is when we've got 1 lone pair and 4 bonding pairs, like we do in sulfur tetrafluoride. It's called a seesaw shape. The bond angles here sort of need to be remembered because they're a little bit messed up. I feel like it would be quite harsh for AQA to ask for this, and I don't think they ever have in any of the mocks that I've sat, but get it on an Anki flashcard and get it remembered. Next, 2 lone pairs and 3 bonding pairs. This is called a T-shaped molecule, like you've got for chlorine trifluoride. The angle is 87.5 degrees. Although we could have 3 lone pairs and 2 bonding pairs, it basically never occurs in nature, and most importantly, it's not on the AQA spec. It would just be a linear shape like this though. Next, we're on to central atoms with 6 electron pairs, the final type you can have. If you've got 6 bonding pairs and 0 lone pairs, you've got an octahedral shape, similar to the trigonal bipyramid, but instead of the base being a triangle, it's a square, 2 wedges out, 2 dashes in, and 2 in the plane, up and below. The bond angle everywhere is 90 degrees. Next up, 1 lone pair, 5 bonding pairs. You get a square-based pyramid. Again, 2 wedges out, 2 dashes in. Next up, 2 lone pairs, 4 bonding pairs. This is a square planar. The bond angle is 90 degrees, 2 dashes in, 2 wedges out. That's all the shapes that ever going to ask you in the exam. The truth of the matter is, this is quite an easy topic. You just need to remember every single one of these shapes, the names and the angles. You'll see so many diagrams between now and your exam though, that it'll become second nature. There's a couple of awkward molecules that I want to bring to your attention. Carbon dioxide and sulfur dioxide. CO2 has actually got 2 double bonds, so it's actually linear, even though you would expect it to be a bent shape. Sulfur dioxide looks like it should be a bond angle of about 107, but no, it's 120 degrees because the electron density in the S to the O is just as strong as the lone pair, so the repulsion isn't more. Something that needs to be added but didn't really fit into the flow of the video is this. What happens if you're trying to find the shape of an ion? Let's take the ammonium ion. We know nitrogen is in group 5, so then we add 5 to the 4 hydrogen atoms that are bonded. That leaves us with 9 electrons. 9 doesn't divide by 2. You can't have 4.5 bonding pairs. But you'll realize that ammonium has got a positive charge. Depending on the charge of the ion, you take or add electrons to that number you've just ended up with. We ended up with 9. I know there's a positive sign, and in your mind you might want to add one, but we know electrons are negatively charged. If we had a molecular ion with an overall charge of -1, we would be adding 1 to that number, which is the opposite of what we're doing here. When it comes to drawing them, you pick the shape depending on the final number you end up with. We look at NH4 and realize there's 4 bonds, and you would expect a tetrahedral shape. And then when we look at ammonium ions, we can see they are tetrahedral shapes. Hope that makes sense. Okay, that's everything you need to know about shapes, and the past 3 videos have indexed everything you need to know about bonding in the A-Level. For videos like this for every topic, notes for every topic, exam questions and more, go to samellisacademy.org. Completely free now, completely free forever. Thank you for watching. See you next time.